All right, so this is the 1.1 warm-up, okay? Number 1 says give 2 other names to line AE. So who can give me an example of a way to name it? Go ahead. EA works. EC works. Okay, anybody else have something different? CE would have worked, right? AC would have worked. CA would have worked. All of those would work on that, okay? Number 2 says give another name for plain S. So if that's one bolded letter that's in the corner, that's one way to name it. What's another way to name a plane?
3 or more points on it.
Good. So what are 3 points that lie on that plane that you could use to name it? Good. DFB works. Okay. Anybody have something different?
You should just say S.
Yeah, like, so when it says plain S, just S alone would imply a point.
Okay.
Yeah, so just be careful. FBE works. You could do something like that. FBE. Any combination of D, E, B, and F would work. All right, 3 says name 3 collinear points. So there's 2 options. What's one? AEC. AEC. 3 points that all lie on the same line. Where's DEB? Okay. And number 4 says name the intersection of line AC and plane S, which would be what? Where does line AC hit plane S? Point E. Okay. Questions? Okay, so let's see. Yeah, so you're listing the points. That's why I separated with a comma. If I write them all together, it's like I'm naming a plane. Okay, so you could have written like point A, comma, point E, comma, point C. But if you're just listing them, make sure you separate it by a comma so you're not mixing that up with a plane. Okay, so start a little bit of 1, 2. The good news is it's not very long. Okay, so we'll see how much we can do. So this is about segments and congruence. Congruence is a word you're going to hear probably from here on out throughout geometry. Okay, so we're going to do some extra definitions today and then a couple of postulates that you're going to use for a long time. Okay, so the first thing we're going to talk about is using the number line and coordinate with a coordinate, which is a letter, okay? Or sorry, with a letter that would name the coordinate. So a coordinate's the number that corresponds to a point. I can draw a number line, and I can give coordinates, any of the coordinates a point, which would be like the name of it, okay? So in this example, -2 is the coordinate of A, 2 is the coordinate of D, 0 would be the coordinate of C, okay? So the number is the coordinate, and then the letter is just the name of it. The first thing you're going to do with these is find the distance between them. So you can either count from one to the other, okay? Or you can take the larger one and subtract the smaller one from it. So if I was to find the length of AD, I would do 2 minus the -2, which becomes 4. Or I can literally count. I can go, okay, from A to D, it's 1, 2, 3, 4. You're probably not going to want to do that if your line is, got 17 points on it, okay? But that is one way to do it. So biggest one minus the smallest one. And then the rule of negatives applies. So if you're subtracting a negative, it becomes positive. We good so far? Okay, a postulate. So you're going to hear the words postulate, theorem, congruence. All this stuff is new to math and geometry anyways. A postulate is the statement or rule accepted without proof. Okay, it can also be called an axiom, but your book will use postulate most of the time. It's basically something that is either simply seen by way of definition or rule, okay? And then eventually we're going to get to theorems in which somebody had to, sit there and prove that theorem. And the first one is called the ruler postulate, which says the points on a line can be matched 1 to 1 with real numbers. So any point on a line can be matched with a real number. And then once the coordinate system has been chosen in this way, the distance between any 2 points equals the absolute value of the difference of their coordinates. which means I can either say the absolute value of the big number minus the little number, or the absolute value of the little minus the big, okay? If the absolute value throws you, then always start with the big number, okay? So if I'd gone back to that last example, I would have said 2 minus a negative 2, or I could have said negative 2 minus 2. As long as it's an absolute value, you're going to get the same answer. So absolute value is just going to make it positive. Okay, so if you would actually picture a ruler in your mind, what's on that ruler? What's a ruler look like? If you were to describe a ruler, if somebody was like, what's a ruler? And you were describing it to somebody, what would it be? It's going to have inches, centimeters, it's going to have measurements on there, right? And it has little numbers on there, yes? So if I take that ruler, right, and I hold it up against a number, against a line, I can give it numbers, okay? So if you think about ruler postulate, picture a ruler in your mind. It just means that I can give any point a numeric value, okay? That's all it means. All right, so adding segment lengths. Remember we said yesterday the difference between a segment and a line is what? Segment stops, and a line never ends and continues. So we can't measure a line, but we can a segment. We can't add two lines together, but we can segments. So when 3 points are collinear, okay, you would say that one point is in between the other two. So it's a terminology you'll see. If I said that C was in between A and B, it means that I have a segment AB and C is somewhere on that segment. Okay? Doesn't mean it's halfway between them. It doesn't mean it's 1/3. It just means it's somewhere on that segment. So on the left-hand side here, you see point B is point B is between A and C, which means B would lie on AC. And E is not between D and F because E is not collinear with D and F. So if it's on the segment, we use the word between. Okay, this postulate you're going to use a lot, so ingrain this in your head. This is called your segment addition postulate. So we know what a segment is, right? And we know what addition is. What's addition? Adding two things. So segment addition says if I take two parts of a segment and I add them together, I get a whole. That's all it is. So if I take AB and BC and add them together, I get AC. Now, in order for the segment addition postulate to work, the word between has to be there. So if B is between A and C, we just said that means what? What does the word between tell you? It's going to be on that segment, right? So if B is in between A and C, then B lies on segment AC. And if that's the case, then AB plus BC is going to give me AC. Okay, so if I take a whole, I divide it into two little parts, I add those parts back together, I should get the whole. So the difference between the word between, right, and saying AC plus BC equals AB, okay? Let's say that that's the case. So this would be your segment postulate. You would need to know that C lies on segment AB. So in order for this to work, I would have to know that AC, or I would have to know that C is on AB. Otherwise, I could just say that, okay, here's A, and here's C, and then here's A, or let me do the other way. Yeah, that was good. Here's A and here's B, okay? There's no telling that makes a straight line. Does that make sense? So technically this way, AC plus AB plus BC does not equal AB, right? They're totally different. So in order for this whole thing to work, you'd have to see the word between, like C is between A and B, or it would say C is on AB. If either of those happen, then you know I've got A, I've got B, and I've got C somewhere in between them. Does that make sense? Okay. So then if that's the case, then I can literally break this up into smaller parts and add it together, which is where the algebra comes back into play. So now let's look here. All right, so this is how you'll see the overlap between the geometric segment addition postulate and your algebra skills. Okay, so this is J is between I and K. So notice the word between, right? So it's telling you that I have a segment that's called IK. And then somewhere between there, I don't know exactly how far, but let's say it's here, is J. This is not drawn to scale. So if I have no idea what the measurements are, it's not IJ might end up being smaller than JK. Okay, it's just a visual. So then the next piece of information I have is that IJ is 2x. So I can say this is 2x. And then JK is 4x minus 6. And then it says IK, which is this whole thing, is 30. So what does the segment addition postulate tell us? Good. Add them and set it equal to 30. So I get 2x plus 4x minus 6 equals 30. And then I get 6x minus 6 equals 30. 6x equals 36, and x equals 6. Now how can I find IJ? Good. So I know IJ is 2x. 2 times 6 is 12. What's one way to get JK? Plug it into that JK, right? So I know JK is 4x minus 6. What would have been the other way to get JK? What do I know about IJ and JK? They add up to 30. So I could have subtracted 12 from 30. You with me? And it's actually a good idea to check both. Okay? Okay, congruent, which is another word you're going to hear a lot in geometry. Okay, congruent are two objects that have the same size and shape. So congruent segments would be line segments with the same length. So in order for things to be congruent, they have to be the same shape. I can't compare a segment to a triangle. I can't compare a square to a triangle. Okay, they have to be the same shape. So when I say that two segments are congruent, one, they have to both be segments, and then congruent means they're the same length. Okay. So you're going to eventually get into congruent angles and congruent triangles. You can compare any kind of thing like that, any kind of figure. Okay, but we're going to start with segments. So the little symbol for congruence is what this is. Okay, it's an equal sign with like a little wave on top of it. Okay, and then the comparison would be if it's equal. So a lot of times these are interchangeable, and depending on the book, some of them are nitpicky about it and some aren't. When you say it's equal, you're usually comparing it like a value. Like AB equals 3 and CD equals 3, so I'm going to say that AB equals CD because they both equal 3. If I'm actually comparing a segment without value, I just know they're congruent. And the way I know they're congruent is this is called a congruency mark. That little red tick mark tells you that those two are congruent. That's usually when you use the little congruent to part. Okay. So if they're equal and they're the same length, then we say that they're congruent. And those little tick marks are called congruency marks. If I had another pair, let's say I had another set of segments, and I wanted to say these two were equal to each other, I can see that they have two tick marks. So 2 is going to match 2, 1 is going to match 1. Usually they're red in the book, but on a test, obviously, they're not going to be red. Your test will not be colorful, unfortunately. It would be lovely if they were. But like a 1 is going to match a 1 and 2 is going to match a 2. All right, so then sometimes, always, or never are like true and false on steroids, okay? It's going to really test your knowledge of something. So when you think of, some people really struggle with this stuff. So sometimes is it possible at all? Then it's sometimes. Always is it has to be, okay? And then never is obviously it can never happen. So this takes sometimes, and as we get a little bit further into the chapter, you're going to see some of these get to be a little bit more tricky. Hopefully not so much now, okay? So number 1 says the length of a segment is blank never. So when I measure something, would I ever say somebody is negative 2 feet tall? Or a line is negative 3 inches? Does that ever happen? Is it possible? No, so that's never. Because if you remember, if we went back a couple of slides, how did we find the length? The absolute value, good, which is never going to be positive. Okay, number 2 says if point S is between R and V, then S blank lies on RV. Always, good, because the word between is there. So if the word between wasn't there, it would be sometimes. And 3, a coordinate can blank be paired with a point on the number line. This is always. So this is the ruler postulate. Okay. That a coordinate can always be given to a point on a number line. Any questions overall? So still not so bad, right?